for those who just joined our session, what I'm going to do is to reformulate the main theorem, at least half of it, the one about the diffusion coefficient, and to start introducing the tools and the strategy the mathematical tools we use for the proof and the strategy we follow. Okay, so let me restart with the equation itself. So we are looking at this anisotropic APZ equation, which is this SPD here. So we have time derivative equals Laplacian plus white noise. We are on the torus of size L, the two-dimensional torus of size L. So X is in TL squared. T is a real parameter, positive real parameter, time. And the nonlinearity, which I call N1, is the following thing. It's a regularized version of D1H squared minus D2H squared. H is not a function, will be is a distribution, or at all times it's just a distribution. So we cannot just differentiate and take the square. What we do is we apply this operator P1, which what it's doing is simply, it takes a function on the torus. Then you take you go in Fourier space, so you look at the Fourier transform, and this operator Pi1 simply puts to 0 all the Fourier modes which are in larger than 1. So it replaces the Fourier transform f hat of k of some function f by f hat k times the indicator that k is smaller or equal than 1, in norm. Okay, and then you get something that is smooth, and then you are allowed to take the derivative to square it. There is no problem. So this is the regularized version of the equation. Okay, so this is the equation, and let me remind you what we want to prove. This is the kind of half of the theorem, in the sense that it's the part about the bulk diffusion coefficient. But I chose to present this one, which is a bit requires slightly less definitions. Okay, so let me recall what this diffusion coefficient is. There is first a 1 in front. So if you look at the linear equation where lambda equals 0, you just get the 1, and it's just a normal diffusion like for the stochastic heat equation, plus another term, which is, okay, there is a lambda square over t times this double integral in time, and an integral on the torus x, an integral in x, which runs on the torus, and then you get the average, the correlation between the nonlinearity computed at time r and position x, and the nonlinearity computed at time 0 and position 0. Since the nonlinearity is smoothed out, it makes sense to compute it pointwise, so there is no problem. Okay, so this is the definition, and let me recall the theorem that we prove with the Giuseppe and Dirk, that for whenever lambda is positive, there exists, there is a positive constant C lambda, and most importantly, a positive exponent delta of lambda, which is somewhere between 0 strictly and 1/2, such that the Laplace transform, which I will rewrite in a second, of this bulk diffusion coefficient behaves for small parameter mu as 1 over mu times a logarithm, power of a logarithm, between log of 1 over mu to the delta and log 1 over mu to the 1 minus delta. And this has to be read as for L large enough, or you have to take lim sup and lim inf. So first you take L large, and then you look at mu small, which is the interesting behavior, because mu small, as usual in Laplace transform, is telling you something about T large. We are interested in large times. Okay, and just to be sure, this diffusion coefficient in Laplace, or function of mu, is simply mu times the integral between 0 and infinity of e to the minus mu t times d of t. Okay, so given the results that was stated one slide ago, what this is telling you in a certain average sense in time is that the diffusion coefficient diverges at like some power of log t. By the way, there was a typo yesterday in my maybe last slide. I wrote that d of t we conjecture to grow it like square root of t log t. no, this t is not there. It's just square root of log t. And we can actually prove log t to some power. We don't get the 1/2, but the t is really not there in this root. Okay, right, so it's even written here. So delta, ideally, conjecturally, delta equals 1/2. In practice, we can prove delta is positive and bounded away from 0 as lambda goes to 0. There is a question. A factor of, well, I mean, okay, so this is the, let's say, okay, the honest answer is this quantity, the Laplace transform of this thing with the t inside is a thing that comes out naturally, yeah, it comes out naturally in the proofs. So if this d bulk were 1, you would just get 1 over mu. Okay, so the Laplace transform of t is 1 over mu. And then these extra logs are telling you that there is actually some log divergence. But yeah, in principle, one could look at the same thing without the t, but it's more convenient technically to look at the transform of t log t times d bulk of t. It's a technical point. Okay, right. So I will now not really the proof stuff, but somehow the preliminary of the proofs. And the first thing we will do will be totally trivial. It's just convenient to do it, but it contains essentially nothing. And it's just reducing from the torus of size L to the torus of size 1. It's convenient because then your momenta in Fourier space will just be integers and not the integers divided by L and stuff like that. So it's convenient to do that. So it's a simple observation that if you define h lowercase of xt to be just the uppercase h, which is defined on the large L, on the size L torus, but computed at x, not at x, but x times L and t times L squared, this little h, that is now defined on the torus of size 1, not L, satisfies the same equation, except that the nonlinearity is changed. So, okay, so this little h solves dth equals 1/2 Laplacian, white noise, plus lambda times nonlinearity, and the only difference is this nonlinearity is that there is an L instead of 1, and simply means that when you regularize in Fourier, you don't cut momenta larger than 1, but momenta larger than L. This is the only thing that changes, and this is an exact identity which can be, I mean, requires 2 lines, but I will not do it. It's simply a rescaling. Nothing more, and the fact that the white noise is exactly invariant by rescaling, because the correlation, the length of correlation is 0. So when you rescale, you don't see any difference. So to be precise, when I say torus of size 1, we actually work on the torus of size 2 pi for, okay, but this is totally technical, just a choice. Okay, so this first step is really nothing. We just shrinked our space and multiply times by L squared. Okay, right. So again, it's just technically, it's just notationally convenient. So the second thing I want to do before trying to explain the proof of the theorem is to analyze with some care, with some, I mean, for those who have never seen it, to see how one solves the linear equation to start with. So the linear equation is simply the stochastic linear equation with additive noise, dth equals Laplacian plus white noise on the torus of size 2 pi. And especially, I want to see that something that is very well known, that the Gaussian free field is stationary. So what do I mean exactly by that? I mentioned last time that the Gaussian free field has to be seen as a Gaussian distribution. So it's kind of a Gaussian, very regular function of x, of the space on the torus, that is centered and such that when you integrate it against, let me call this Gaussian free field eta x times some test function on the torus. This is a normal random variable that is centered and whose variance is the h-1 norm of phi of the test function. So like phi minus delta minus 1 phi. Okay. Okay, but let's see it more explicitly. When you go to Fourier space, this is much more explicit. Another way to see the Gaussian free field on the torus is to say the following. look at the Fourier component. So K here is okay. It's written here. K is a vector. Is in Z2. I mean, we are on the torus of two-dimensional torus. So the momenta, when you decompose any periodic function of the torus, the momenta will be have integer components. If you look at the Fourier component K of this Gaussian free field, so it's just the integral of on the torus of e to the minus k I k x h of x, which makes sense because, I mean, exponentially certainly an allowed test function is totally smooth. This thing here is a Gaussian random variable, but importantly, this random variable, these Fourier components of the Gaussian free field are independent for different k. Okay, so you can characterize the Gaussian free field as follows. Its Fourier components h hat of k are not IID, sorry, they are independent. They are center, and their variance, their covariance is the average of h hat k, h hat l is just, there is a Kronecker delta that k plus l equals 0, and then times 1 over k squared. This just comes from the fact that when you apply minus the Laplacian inverse to the plane wave e to the ik, you get the 1 over k squared. Very good. So from here you see that okay, the fact that here you have not a Kronecker delta k equal L, but k equal minus L is simply because the plane waves are complex. They are not sines and cosines, but are complex. Okay, but this is it. And the other thing you see from this formula is that if you take k equals 0, so the zero mode is not well defined. It's a Gaussian random variable of variance 1 over 0. So the zero mode of the Gaussian free field, as I already said yesterday, is not well defined. So you should always think of all the modes except 0. Okay, very good. So right. So why is this Gaussian? So what I'm claiming is that if you start your initial process, this linear process from this Gaussian free field distribution, it's at all fixed times, at all fixed later times, your measure is still that of the Gaussian free field, and this can be seen quite easily in Fourier space. So you take the equation, which is here. No, it was here. Oh, sorry. Which is here, and you just apply to the left and right hand side the Fourier transform. Okay, and then you get an equation for the kth mode of your function h. And what happens that in Fourier transform, all the modes now become decoupled. So what you get in Fourier transform is simply that time derivative of the kth mode of your height is minus 1/2 k squared, which comes from the Laplacian, the same mode, plus a white noise in time only. Now space has been integrated away because we have taken Fourier transform. So, and this bk b dot k is a white noise in time that is indexed by k. It's independent for different k's, and they are IID. So it's just a usual white noise in time. It's a derivative of the Brownian motion in time, and it's independent for different k's. Okay. So what is important here is that when you go to Fourier transform, all the Fourier modes now are decoupled. Each one lives its own life. You see there on the right-hand side, there is only h hat k for the same k as in the left-hand side, and that's it. So they are a set of independent Ornstein-Uhlenbeck processes. If you start if initially the modes are independent, they stay independent forever. They don't see each other. So in particular, I mean, these are Ornstein-Uhlenbeck processes. If you remember the stationary state of an Ornstein-Uhlenbeck process is, you will see that simply in the stationary state is that this h hat of k will be center Gaussian random variables of variance 1 over k squared, which is exactly the law of the Gaussian free field in Fourier space. So this is why. This is a very simple computation that shows you that for the linear equation, the linear equation preserves the Gaussian free field on the torus. Okay, so it's as simple as that. Okay, so this is one thing. And now we would like to go back to the nonlinear equation. So the first thing I will do here is to discuss what the generator of the process looks like. And And I will discuss why it is the case that also the nonlinear equation will preserve the Gaussian free field, which is, as I said, is not a trivial fact. And here it is here that one uses that the matrix U has been chosen to be diagonal 1 minus 1. Okay, so before coming to the stationarity of the GFF, let me discuss a little bit more about this Gaussian free field. So now I denote the Gaussian free field as eta, not h. H I want to see h as the space-time process, and eta just as a process at a fixed time. So I'm just looking at, say, time 0 or any other time. I have a Gaussian free field, and I call this random distribution eta. Okay, so for a couple of slides, there is something which is very canonical, probably is known to maybe most of you, but okay, I want to anyway to recall this. So there is you have now this Gaussian free field, which you can see as a collection of independent Gaussian variable eta hat of k, which are independent and have variance 1 over k squared. Okay, so if you look at the space L2 of eta, that is the space of all functions which have as an integrable second moment, it's well known that you can decompose that space into an orthogonal sum of spaces, of subspaces Hn. This is called the Wiener-Chaos decomposition. Okay, in such a way that all the spaces with different index n and m are orthogonal. So if you take two functions, one in Hn, one in Hm, and you take the scalar product here, it will be just the expectation according to the law of the Gaussian free field of a function f times a function g. Okay, so this will be 0 if the two functions belong to two different subspaces Hn, which are called the chaos. Chaos n and chaos m. Okay, so the way this is done is quite intuitive. So you have a family of Gaussian random variables, eta k's, where k ranges in Z2. Okay, it's an infinite family, but this is not a problem. What you could think of doing is to group, to decompose your space. Of course, once you have Gaussian variables, natural L2 functions are momenta, like polynomials in these variables. Gaussians have momenta of all orders, so any polynomial in these Gaussian random variables will be a function in L2. So these are very natural functions to build these spaces. And what you could think of doing is to say that Hn is this subspace of L2, which is spanned by all monomials of order n. This would be a natural attempt, but it's not exactly like that, but almost. So the way it works is, well, the first space, H0, indeed is just the space that contains the constant. So it's just a constant random variable, is the constant, nothing very interesting. H1 will be the subspace generated by the eta hat. So an element phi1 in H1 will be of the type a sum over k of certain coefficients, say real or complex coefficients, say ck times eta hat of k. Well, you want this sum to converge, but otherwise it's a linear combination of the eta hat k. And then the Hn will not be a linear, not just be a linear combination of monomials of order n, but will be a linear combination of Hermite polynomials of order n. And for those who don't, probably maybe all of you know this, but let me just recall how this construction is done. It's done essentially. You would like to take in the chaos of order n the monomials of order n, except you want to make these also orthogonal to the other subspaces H0, H1, H2 up to Hn minus 1. So for instance, let's do it maybe in this example. Suppose I take the product of H hat k, H hat L. It's a monomial of order 2. Clearly, it's orthogonal to any variable in H1 because, I mean, if you take the product, you get a monomial of order 3, and it has average 0 because the Gaussian variable are centered. But on the other hand, this thing here, this product of two variables, is not orthogonal to the constants. If you take, I mean, the average is in general not 0. In fact, it's not 0 if k equals minus L. But there's a very obvious way to fix that. So if I define a new variable which is eta hat k, eta hat L minus the average, clearly now it's 0 is centered. And now, in fact, now this variable is orthogonal to the space H0. And I define this recenter thing as the Wick product of H hat K and H hat L. So, and you can do this in general. So given a monomial H hat K1 up to H hat Kn, there is a way to make it orthogonal to all the other causes defined before, and that is called the Wick product. And in general, it's more complicated than just subtracting the average, because you want to make it orthogonal not just to the constants, but also to all the other causes. Anyway, what I want to say is that, okay, maybe here I should, yeah. So what this is saying is that any function in L2 can be written as a decomposition like this, as a sum over this order of the chaos from 0 to infinity of Fn. Fn lives in the chaos of order Hn, and you should think of Fn as a given by a sum over indices J1, Jn in Z2 of a certain kernel phi n G1, Jn of the Wick product eta hat J1, eta hat Jn. Okay, so you can equivalently see f as a function in L2, or you can look at the kernels phi n. It doesn't make a difference. It depends if you prefer to work in L2 or in what is called the Fock space. So, and again, when there will be some operators later acting like a generator, acting on functions in L2, you can either see it as acting on function in your probability space if you are more comfortable to live in probability space, or you can see there's operator acting on the kernels, which are just symmetric functions of the indices. Okay, is this okay? So presumably this is well known to many of you. So just remember, there is a natural way to decompose our probability space of the Gaussian free field into this so-called Wiener-Chaos decomposition, which is an orthogonal decomposition. And this structure is important because it will be very important to see how the generator of the stochastic process will act on the different components of this decomposition. All right, so yeah, we will see how the generator acts on each of these subspaces. And okay, so to see that, the first thing one does is to rewrite the AKPZ equation, now the nonlinear one, in Fourier space. You have just to take the equation, you integrate, you multiply by e to the IKT, right and left hand side, integrate over x, and then, sorry, e to the IKX, integrate over x, and then you get on the left hand side the derivative of the time derivative, if you want, of the Fourier mode number k. And on the right-hand side, you get something. And this something, of course, there is this red part, which is the linear part of the equation, which we just obtained before, minus 1/2 k squared eta hat, h hat, plus the white noise indexed k. This was already there in the linear equation. And then you get the nonlinear part. I mean, I will not do the computation, but you have simply to take the definition of the nonlinearity. There was the function, it was regularized in Fourier, then there was a derivative, then you took a square. I mean, you have just to rewrite this in Fourier space and you get to some expression, which I will write in a second, in the next slide. I will not do the computation, but it's really trivial. And okay, so to start with, the nonlinearity was quadratic. So it looked like something like dh1 squared minus dh2 squared. So it will be still quadratic in the Fourier components, no surprise. And what is bad, in a sense, what makes the business complicated is that it will couple all the Fourier modes. It is not anymore true for the nonlinear equation that the modes are decoupled. Otherwise, life would be easy and the equation would simply be Gaussian. So all the modes are now coupled. So you get, in principle, an infinite system of coupled stochastic differential equation, one for each mode. Actually, okay. So let us write it down. So how does it, no, this is the slide before. How does this nonlinear part in the equation look like? Well, it looks like this. We're looking at the equation for the mode index k. The nonlinear part looks like there is a sum of the modes L plus N and M, such that their sum makes up k. Then there is a certain coefficients, which I will write in this, is written in the next line. And then there is a product of the two modes h hat L, h hat M. So it's, as I promised, it's quadratic in the Fourier components. And this coefficient K large L just reminds you that the cutoff in Fourier space is large L. That is the only place where the L survives, but it's important. And then depends on these two momenta, L and little m. And it looks like this. If the momenta L and M are pairs of integers, no? So L is L1, L2, and M is M1, M2. So these coefficients of this nonlinearity is L2, M2 minus L1, M1, and this minus comes from the minus in the matrix, times, and then there is simply the indicator that all these momenta L, M, and L plus M have to be smaller than smaller than L. And this simply comes from the cutoff from the operator PL, from the regularization thing in Fourier space. So if you look back at the expression for this nonlinearity in real space, here it is. No, it's not here. Where is it? Yeah, you see it's here on the bottom. You see there is the cutoff acts 3 times. It acts on H, then you differentiate, then you take another copy of it, and then take the square. It's already acting twice, this cutoff, and then again it's in front. So this cutoff acts 3 times, and this is why in this expression you get this indicator function that imposes that, where is it? That imposes that all 3 momenta L, M, and L plus M are smaller than L. Okay, but again, this is a computation you can do quite easily. Just requires a couple of minutes of patience. But again, it's important that this minus sign is there because of our choice of the matrix. Very good. So okay, so let me the first result I want to present, which is the proof is taken from this earlier work by Giuseppe and Dirk and Philip Schönbauer, is telling you that this equation, this nonlinear equation, for every cutoff L and for every choice of lambda, preserves the Gaussian free field, which is not a trivial thing. And actually, this was actually known before, at least in a more formal way. Actually, yesterday Alexei sent me a paper by De Silveira and Cardar, where they have, they look at the same equation, they don't regularize. So the argument is a bit formal, but the idea that the Gaussian free field is stationary is perfectly there, and the idea of the proof is in a sense quite similar. Okay, so very good. So basics of Markov processes. If you want to check that a certain probability measure is stationary for a Markov process, what you want to do is to take, well, this, if E denotes the average with respect to this distribution, what you want to do is to take the generator of your Markov process, apply it to any function on which it's allowed to be applied, and then you want to prove that the expectation of this is 0 for every function f. Okay, this is what we want to do, and to do that, it's useful to look more precisely at how the generator looks like, how it acts on this Chaos decomposition. Okay, we have, as I said, we have a system, a coupled system of stochastic differential equations. So it's simply an infinite system of coupled diffusion equations, each one with its Brownian motion bk, and they are coupled together by this term m. So when you have a diffusion process, you can read the generator of the process quite easily from the equation. So if you have, okay, maybe I want, okay, maybe I can, I don't know. So maybe this is totally well known to everyone, but if you have a diffusion like dxt, so x is a vector, x is a x1 up to, I don't know, xn, t equals some drift term b of xt dt plus, let's say, to be simple, b dot t, where b dot t is a vector of n independent Brownian motions, then by Ito formula, the generator L will act on a function of this thing as follows. You take a sum over the components I of bi times df dxi. So there is the drift terms gives you x as a first order derivative. And then there is the Ito term, 1/2 sum over I of the second derivatives of f. Okay. And this is for usual diffusion. Like here, there is a slight complication due to the fact that these Brownian motions are actually complex. But I mean, it's a minor complication. And in fact, if you just apply this Ito formula to our equation, what you find is that the way the generator looks like is that it's decomposed. Of course, you can decompose it into the generator of the linear term of the linear equation plus an extra term. We call L0 the generator of the linear equation, and the extra term we call it lambda times A. It's called A for a reason, because it will be antisymmetric. This will I will say in a second, but that's why it's called A. And well, how do this operator looks? How does this generator look like? If you just look for a couple of minutes to the equation, you will see that the way it acts is as follows. So first of all, the generator of the linear equation. So you have to think that you want to apply these generators. They act on functions of your random variables. So they act on function f of, in principle, all the Fourier modes eta hat k for k in Z2. You have to think of, to make things well defined, to think of cylindric functions which depend only on a finite number of Fourier modes. So you take a function, a smooth function of the Fourier modes, of finite number of them, any number, and you want to act with this L0 and A on them. And the way it acts is as follows. So the linear part is very simple. It just, it acts as a sum over all the modes. Then you take the derivative of f with respect to the mode k. So this is what it's saying. And then remultiplied by eta hat k times minus k squared. So it takes f, think of it of being a polynomial. Depends on many variables in principle. When you act with the generator of the linear process, it just take a sum over all possible components. You take the derivative of f with respect to that component, remultiplied by eta hat a, k, times this constant minus k squared. Okay, and then there is a plus and other terms which corresponds to the Brownian part in the process, which is the second derivative of h. So which corresponds to this term here, this Ito term. So there is a second derivative of f, once with respect to eta hat k and once with respect to eta hat minus k. So this is because of this complex structure, this complex value of the Brownian motions. This is the linear part of the generator, and the one which the one coming from the nonlinear part of the equation, A, acts in this other way. It's also easy to see. It acts as follows. You act with A on F. What it spits out is a sum over L and M of this coefficient KLLM, which appeared already here. This function here, which is just a function of the momenta. There is nothing random in it. Okay, times eta hat L, eta hat M, and then the derivative of F with respect to L plus M. So this again, this is so as you see this A is changing the order of the chaos. So if F, for instance, is a monomial of order 3, for instance, you take a derivative with respect to eta hat of L plus M, so it becomes a monomial of order 2, and then multiplied by 2 other eta, so it becomes of order 4. So it's changing the order of the polynomial. Okay. So this is how the generator looks like. And again, if you want to prove that this is already mentioned, if you want to prove that the law of the Gaussian free field is invariant, you should just check for every cylinder function f that the expectation of the generator times that function applied to that function is 0. Now, for the linear equation, we already know that this is the case because we already checked. That it preserved the Gaussian free field. So I will not recheck it now in this new language. So we know already that the expectation of L0 applied to F is 0 for every F. And now we need to check that also the nonlinear part, the extra part of the generator satisfies the same identity. So it could have happened that, so I see there is a question. No, there is just, okay. It could have happened that the whole generator L plus A preserved the Gaussian free field, but not the two separately. That would have been more complicated miracle, but it turns out that both of them preserve the Gaussian free field. Okay, so so how do we check this? How do we check something like this? Well, it's quite simple, but it's at that point that some miracle at some point happens. So let's see. What we want to check is that. So let me first recall the trivial fact, which is the Gaussian integration by parts. Suppose you have a family of Gaussian random variables, finite or infinite, doesn't really matter, and they don't need to be IID actually. They can be correlated. And then you want to take the expectation of one of them, this, let's say eta hat of L, times a function of all of the family. F can depend on the whole family. Then the integration, Gaussian integration by parts, telling you that this, okay, supposing that F is decays enough so that the expectation is finite, this expectation is given by the sum over all the random variables of expectation of the derivative of the function F with respect to the variable number M times the covariance between the variable index L and the variable index M. So L appears here, it's not summed. What is summed over is M. And this is it. And in our case, in our particular case, this covariance here is very simple. It's 0 unless M equals minus L, and then it equals 1 over L squared. And now what we want to do is to compute expectation of A applied to F, but A applied to F, you see it here, is just exactly of this form. So it's eta times derivative of F. So we want to apply this integration by parts. So what we want to check, what is expectation of AF, is just this thing here, is a sum over L and M of this coefficient times expectation of eta hat L, eta hat M, derivative with respect to L plus M of F. Okay. All these are random variables. And now we want to apply this integration by parts twice. The first time we will look at eta hat M plus times the derivatives as a certain function, which earlier was called F, and then we applied it twice. So you apply this identity twice. I will not do it, but it's really a computation. And you get the second line. Again, the sum survives, of course. The coefficient K has gotten now a tilde, which simply means that it's now divided by L norm of L squared, norm of M squared, which come from this, from this covariance. Okay, and that's it. And then in the expectation, now you have a third derivative, simply because you had one to start with, and when you apply integration by parts, you get two other derivatives. So now it looks a bit complicated. You have the expectation of this third derivative of F, and you would like to check that this quantity is 0 for every F. So clearly there must be some symmetry for this to be true. And the symmetry is the following, that, okay, I've just rewritten this expression. The symmetry is simply that, you see, this third derivative is invariant when you change, when you map ML into M comma minus M minus L, and at the same, or if you do the mapping ML to minus M minus L comma L. So if you do this change, this third derivative is clearly invariant. So you can symmetrize over these permutations. And on the other hand, it turns out that if you take this coefficient K tilde that depends on LM, and you sum these three symmetrizations, you get exactly 0. This just comes from the explicit form, from this minus sign. I mean, it might not be totally obvious, but it's the case that this sum of these three terms is exactly 0. Okay, so it's here where this little miracle happens. Okay, and by the way, as I mentioned, there is this paper by Cardar and De Silveira, if I'm not mistaken, where they obtain the same, also earlier, the invariance of the Gaussian free field for this equation. They don't do it in Fourier space. What they remark is that this invariance can be seen as an effect of a symmetry of the system in real space without going to Fourier space. What you can see starting from the equation that it satisfies the following symmetry. H is changed to minus H and X is changed to Y. The isotropic AKPZ equation does not have this symmetry, but the anisotropic one does. When you change A to minus H and at the same time change X to Y, the equation stays the same. And the effect of this symmetry in Fourier space is exactly this little miracle here. Okay, so okay, I think it's nice to see that somehow it's kind of surprising that the anisotropic equation looks less symmetric than the isotropic equation. In fact, it loses the symmetry X to Y, but it gains this other symmetry, which saves the Gaussian stationary states. Okay, so I hope this is clear. Right, so we have checked that the Gaussian free field is preserved by the AKPZ equation. This is good, because without that, honestly, we wouldn't know what to do. Okay, so now before proceeding, we would like to, now we know that that this Gaussian free field is preserved, we would like to look more precisely at the structure of the generator, because that will be essential in the proof of the remaining result. Again, the generator decomposes again in the generator of the linear process plus the rest, the nonlinear part. And I just rewrite here the two expressions. The first thing you can see is that we would like to see, I mean, now we know that our L2 space can be decomposed in Wiener-Krauss decomposition. We'd like to see how these two parts of the generator act on each component of this decomposition. And what turns out is that the generator of the linear equation acts very simply. In particular, it preserves the order of the chaos. If you apply L0 to a function in the nth chaos, you get a function in the same chaos. And more than that, it acts diagonally in Fourier space. So I will make an example in a second. While A will act in a more complicated way, it will change the chaos. So if you start from a function in the chaos n, it will not spit out a function of the chaos n. So somehow the chaoses, I don't know what is the plural of chaos, are all coupled together. And this is what makes the problem difficult. Okay, so maybe let me make one example just to show that there is nothing exotic in this about this. So how does L0? Oops. How does L0 act? So I want to act on L0, for instance, on a function on the second chaos, which is eta hat k, eta hat minus k Vig product. Remember that Vig product here just means subtract the average. And remember that L hat acts as a sum over k primes, or there is 1/2 minus k prime squared, eta hat k prime, d respect to eta hat k prime, plus d eta hat k prime, d eta hat minus k prime. This is how eta L0 acts. So now you want to apply this to this particular function eta hat k. Okay, from now on, I will not say hat, otherwise I lose half of my time saying hat. So eta k, eta minus k, I want to act with this operator. So, and when you do that, what happens is that when you act with this first derivative, you end up with just one eta, but then you remultiply back, okay? And so what happens is that this first part will give you, believe me, minus k squared twice plus k squared eta hat eta, I promise, but anyway, eta k eta minus k. And then the second part, you're taking the second derivative of something which is over the 2, just gives you a constant. And what it gives, Just a second. Oh, yes. It gives you simply, I think I forgot a factor 2, and they should give you just a +1/2, maybe a +2/2. Okay, so if you put things together, you just get 1/2 of, and then you multiply by this twice k², and then you get exactly what you started from. Maybe I also want to put a minus here. Sorry, minus, and then you get 1/2 eta k. I'm sorry, here I'm making a kind of a mess. I want to have the 1/2 in front, and then inside here, what I get is simply eta k, eta minus k minus 1/k². Because here you get in the first term, you get the k², in the second not. So if I put out the k², here I get 1/k². And this is nothing but the thing we started with. So you see, not only L0 here, it takes as an input a function in the second cause and gives you out a function on the second cause, but actually it acts diagonally if you are in Fourier space. It just gives you the same variable simply multiplied by an eigenvector, an eigenfunction, an eigenvalue. Okay, so in the L0 acts diagonally in this Gauss decomposition and diagonally in Fourier, and acts as a Laplacian. It just gives like the Laplacian. If you apply it to the eigenfunction of the Laplacian, it just gives you k². This is exactly what it's doing, and I suspect I'm forgetting a factor -1. Okay, so L0 is very simple. Acts diagonally in Fourier space, preserve the order of the Gauss. I've just shown it in one example, but it's true in general. And what about the nonlinear part of the generator? Here I will not make the computation. It's a bit more painful, but it's also not hard. What one can prove is that the nonlinear part, if you take the nonlinear part of the generator and act on a function in the nth Gauss, it spits out a function which is a superposition of a function in the Gauss of order 1 more, and plus, so the image of this operator will be in the union of hn-1 and hn+1. You might have guessed that this nonlinear part increases the order of the Gauss because you see when it acts, it takes one derivative and then multiplies by 2 variables. So it's like increases the order by 1. But the elements of the nth Gauss are not exactly monomials, they are Hermite polynomials, so it's not so surprising that it does not only increase the Gauss. It spits out a part in the Gauss of order 1 or above, plus a part in the Gauss 1 below. And even to prove that, you have to use this cancellation. So if in general, if you take another matrix, it will also spit out a component in the Gauss n-3, if I'm not mistaken, and that would spoil the whole thing. Okay, but this is true. And then you can decompose this operator into the part which increases the Gauss, which we call A+, and the part which decreases the Gauss, which we call A-. So by definition, A+ maps Hn into Hn+1, and H- maps Hn to Hn-1. And what you can see is that the A+ is just the adjoint of minus the adjoint of A-, in the sense that if I take, like here, if I take a function g, I act on it with A+, then I multiply by another function f, and I take the average. This is the same thing as minus take the average of A minus f and then times g. So it's minus the adjoint of A+ is minus the adjoint of A-. Altogether, this nonlinear part of the generator is antisymmetric. Its adjoint is minus itself. So it's really the antisymmetric part of the generator, while the generator, the L0 part of the generator is symmetric, corresponding to the fact that the linear equation is a reversible Markov process. The nonlinear equation is not reversible, and what makes it non reversible is exactly this additional part. Okay. All right, very well. So I keep an eye on the watch. I keep an eye on the watch, which shows that essentially I'm done, right? Is it correct, or how?
Well, but there was a mix-up with the.
Yeah, I mean,
version. You can take more time if you need it. It's fine.
Yeah, let me see. Okay, so yeah, I will take a few more minutes and then I will try, I will find a reasonable place to stop before the really, maybe, yeah, I will do so. I will continue with some soft stuff and then the hard stuff will come tomorrow for those who are still alive. So now what we have done is to study the structure of the generator. We have identified the symmetric part, which is just a generator of the linear process, the antisymmetric part, which is the additional part. We've seen how it acts in this Fock space. The next thing to do, we abandon for a moment Fock space. We just massage a little bit the bulk diffusion coefficient to have it to have a more manageable form. And then once I have massaged it, maybe I will just postpone to tomorrow. So here I've just rewritten the definition of the diffusion coefficient. I have multiplied it with t, so that the first term is not 1 but t. Okay, and then you have this part that contains a double integral of correlations between something at time r and at position x and something at time 0, position 0. This was defined in terms of the original quantity large H, which is defined on the size L torus. But now we have moved to the size 1 torus. And by a simple rescaling of space and time, extremely simple. If you do this, if I apply this rescaling here, what you obtain is the second expression, which looks kind of the same, except that there is an L squared coming in front. The time t is replaced by t over L squared, and that's it. And now the integral is not on the torus of size L, but on the torus of size 1. So here nothing has happened. And the second observation one can make and then is when you have this kind of integral from 0 to t ds, integral from 0 to s of something that depends on t minus s, you can rewrite as 1/2 of the square of the integral itself. Well, okay, so the statement that is true is the following one, that this bulk diffusion coefficient can be written as t plus this lambda squared L squared times the average of the square of something, and this something is simply the integral from 0 to t over L squared of the nonlinearity. Okay, so really the bulk diffusion coefficient, the diffusion coefficient is the one of the linear equation t plus something that is simply, I emphasize, just the variance of the time derivative of the nonlinearity. So you take the nonlinearity, integrate in space and time up to time t, take the square of that and average. It's easy to see that the integral itself is a center random variable, so it's really variance. Okay, so this is, again, requires just one line of computation, and finally you take the Laplace transform of this. It's a sum of two terms. You get two terms in the Laplace transform. When you Laplace transform t, you just get 1 over mu, and when you Laplace transform the other thing, you get another object that I call B, and that will be our main object of interest, because our goal is to understand how this extra part is larger than the linear part, gets these extra log corrections. So, and if you do this computation, what you come out with is that this B of mu is nothing but, let me read it and then say where this expression comes from. So you get a 1 over mu, which is there also in the trivial part. Then there is expectation of NL is the nonlinearity of the equation. Expectation is with respect to the Gaussian free field. So like it's an expectation at time 0 if you want. Then there is a nonlinearity. Then there is the inverse of mu L squared minus the generator. So there is an inverse here, which makes the whole thing difficult. And then again times applied to N itself. So it's kind of take the inverse of the generator and then sandwich it between the nonlinearity left and right, and then take the average. So first observation is, how does that come from? Simply when you have the correlation between a quantity at time t and a quantity at time 0, you can write it as an expectation of the thing at time 0 times times the semigroup e to the t L times f. So now you have reduced to a computation at time 0, but there is a e to the L t times the generator. And then morally, when you take the Laplace transform, you get the e to the minus mu t, but there is also this plus lt. So if L were a number, clearly you would get just 1 over mu minus L, but this you can do also when L is an operator. There is no problem in this inverse simply because since L is the generator of a Markov process, its eigenvalues will have a real part which is negative. So this thing is invertible. There is no issue there. But the point is that this inverse in general, we don't know what to do. Okay, so hopefully you're convinced that this formula might be true. It's one line. It just uses these two facts that I've listed here. And right now, so I get maybe to the point where I can make a stop. So and finally we can start actually working. For the moment it was just preparation in the sense that we have reduced our study to looking at this quantity here, studying this inverse of the generator, taking in sandwich between the nonlinearity, and trying to prove that when this parameter of the Laplace transform goes to 0, this thing behaves logarithmically in log over 1 over mu, log of 1 over mu. And of course, the difficulty is that there is, while the generator, as you saw, so the generator of the linear equation was extremely simple. It acts diagonally in Fourier space, so it's trivial to invert it. In Fourier space, the L0 acts as multiplication by k squared, so the inverse is just multiplication over 1 over k squared. So L0 is easy to invert, but L is not easy because it mixes up all the causes and it's not diagonal in the Fourier space. So there is no easy way to invert it, and this is where all the works will happen. So I think this is a good place to stop. Tomorrow I will start with section 6, so somehow is where the real works begins.
All right, let's thank Fabio.
Thanks.
And then there is already a question in the chat for you. So.
Yeah, I mean, miraculous. Well, it's a symmetry. So I don't know whether you like more Fourier or real space, but in this work by Cardar, they see it as an effect of this symmetry of h to the minus h and x to the minus x to y. If you formally write down the Fokker-Planck equation and you impose that the Gaussian free field is invariant, you will get in the end that something vanishes if the two lambdas are 1 and minus 1. I mean, it's not so intuitive. I wouldn't say it's intuitive. So it remains a small miracle. Whether you see it in Fourier space or in real space, it remains a little miracle. Again, it's not reversible, so you're not guaranteed a priori that you have that you can guess the invariant measure. Okay, so in particular, if you take, okay, here is a free slide. If you take Q, which is not 1 minus 1, but is I don't know, 1 minus 2, which should belong to the same universality class, in that case, the Gaussian free field is not preserved. And actually, one nice thing that I just learned this weekend, looking at this, not weekend, yesterday actually, looking at this work by Cardar, is that, for instance, if you try to impose the same condition in dimension higher than 2, so in dimension 3 and higher, you cannot find the matrix such that the Gaussian free field is preserved. You just don't manage. And in dimension 2, all the cases which preserve the Gaussian free field is this matrix 1 minus 1 or any rotation of it. Yeah, so it's still it's a small miracle.
They do in this paper of Silveira and Cardar, they introduce some higher dimensional systems that have Gaussian steady state, right?
They certainly introduce some cases of more coupled equations where they are Gaussian. I had the impression that if that in dimension higher than 3 and higher, they say that, at least when you have a single scalar function, I think they say explicitly that there is only that only the trivial case preserves the
okay. So it's coupled equation.
Yeah. Coupled equation, you can construct some which actually even formally they construct coupled equation in 1 dimension 1 or 2 which preserve Gaussian fields. I didn't know that actually about this. But anyway, so but in dimension 3 and higher, apparently there is nothing, and yeah, it's nice.
There is another question in the chat.
No. Well, no. Nothing explicit. I mean, I cannot write down the semi-group PT H prime explicitly. I mean, that would be great, but no. Otherwise, I could read from that probably the time correlations directly. No, so it's apart from writing it like this, no. I would say no. If you mean something explicit, of course. Okay. Oh, and maybe I just wanted to answer a question that was asked yesterday, and I think I didn't answer properly. It was asked whether, if you look at the isotropic 2D KPZ equation, and if you rescale time, like, I don't know, time over a square root or log of something, I get the same scaling as Caravena, Ziguras, and soon Luket or Castel-Sai, etc. No, the answer is not. You cannot just obtain that scaling by rescaling time. In that case, maybe you get you get 1 over square root of log epsilon in front of the noise, but you also get it in front of the Laplacian, so which is not the scaling that is done there. Okay. So somehow if you just rescale time, you get something more difficult. You get an equation where the noise is going to 0, but also the Laplacian is going to 0, so it's much more irregular. So it's another scaling.
Okay, let's thank Fabio again. Fabio will give one more lecture tomorrow at the same time, 11 in Eastern US. And the next talk is going to be by Greta Panova, and this is her first lecture. And what we will do, we will close to try to avoid the creation of phantoms. We'll close this window, and then you would need to reconnect using the same link. I don't know if it's going to help or not, but we'll give it a try. So Ivan posts the link in the chat.
Let me post. That was the website. Let me post a better version.
Oh, that's the website, right? Okay, so one can get the link from the website if you don't have it saved anywhere.
Here, let me. Here's the link. You can copy it into.
Right.
Whatever.
And there is a link in the chat as well. So Greta is scheduled to start in something like 17 minutes or 18 minutes.
I have a question. When will recordings be available?
So the recordings for yesterday are already posted. Yours and Hugo's, along with the slides you guys provided, and probably
Thanks.
Later today, the ones from today.
Okay.
Okay. So I'm gonna.
Okay. So let's close the session and then see you in a second.